Hello. Wherever you're listening from, I hope you and your loved ones are doing very well. I'm Shayon. I'm a grad student working with Dr. Axel Vanderwall at Brown University, Rhode Island. The title of this talk is Rapid Screening of High-Throughput Ground State Predictions and can be broken down into roughly two discussion points. First, we shall demonstrate a semi-automated software pipeline that can be used to plot approximate phase diagrams with incrementally tunable accuracies completely from first principles, without any experimental input at any stage of the process. Next, once we do plot a phase diagram, more specifically the iridium-ruthenium binary alloy, we shall see that our technique helps resolve a past experimental and simulation discrepancy regarding the absence or presence of certain ordered phases. But before we go on to describe the process, we need to introduce the model which we use for our calculation. First step of that is to describe the phase, for which we use the compound energy formalism developed by Matt Sillett. It's a generalized phase description where the composition and constraints could be set independently over sublattices, such that these sublattices then compose together to form our actual phase. So the figure on your right describes a general phase as per CEF. We have two sublattices, sublattice 1 and 2. Sublattice 1 can have A or B type of constituents, while sublattice 2 can have D, E, or F. We also have the concept of site fraction, which is the fraction of sites occupied by a particular species on a particular sublattice. By definition, they sum to 1. A good example of this nomenclature would be the NaCl structure that can be understood as a two sublattice system, each sublattice being an FCC lattice by itself, with the two origins of the sublattices shifted by 0.500 with respect to a global coordinate. There are also two keywords or definitions that we should keep in mind. First is the N member, which is the structure that has only one element in each sublattice. And a simpler version of that is the unary N member, or a pure material, where each sublattice is occupied by one and only the same type of constituents. We can now use this phase description to define the energy of a particular solid solution of a given phase. This model, which is known as the CalFAT model, is a generalization of the regular solid solution model. It is instructive to understand it by taking a concrete example. So let's take this two sublattice system of 6 and 2 sites per sublattice respectively, where any site can be occupied by both iridium and ruthenium atoms. Here we can write the individual equations as first the reference free energy of mixing, which plays a crucial role as they act as support to the free energy surface. They are in a way the fundamental unit which are being mixed together. Then you have the configurational entropy term, with the catch being that the Stirling approximation for the total number of combinations, the x log x sums, is limited to exchanges only between sites within each sublattice in which that particular constituent sits at. Then you multiply them with the total number of sites per sublattice to get the total entropy of the phase with the correct scale. And finally, we have the excess free energy, which accounts for the interaction of the constituents by virtue of being in a solid solution together. These parameters, the L's, also called the Redlich-Kiste parameters, account piecewise for the pair interactions, three-bond interaction, and so on and so forth, and is that piece of the model which is up to the researcher to decide the complexity of. The example here shows only up to order 2 for sublattice 1. That is, we only account, in addition to the N members, the excess free energy as a result of interaction between two atoms present in sublattice 1 only. So, with the setup out of the way, let's talk about the software steps. The main phases considered in this calculation are the FCC, HCP, and the ordered counterparts L12 and DO19. We also have a liquid phase and certain phases that are not energetically competitive with the primary phases, and those are simply modeled as 9 compounds. A slight note about the liquid phase. Our group is currently working on an SQS of the liquid phase, which is a difficult problem due to the lack of long-range symmetry. So in this case, we instead performed ab initio MD on pure and 50-50 compositions to obtain the equilibrated energy of the liquid phase above the melting point of the constituent species. Before we dive into the details of the pipeline, here is the big picture so that we have a foresight of where we are going with the steps. Step 1 is to decide the phases, the compositional grid on which we shall perform our DFT calculations that will then be fit to the CalFAT model to find the general energy expression. In this code, the SQS to TDB, we assign the compositional grid as the levels, and the -L term denote all the phases that we intend to include in our calculation. Now, once the 0 Kelvin formation enthalpies are found, we calculate the vibrational enthalpy of our system by generating symmetrically distinct perturbed structures around the ground state for each of the data points, calculate the static formation enthalpy of each of these perturbations, and then we fit it to a harmonic or an anharmonic spring model to obtain the vibrational enthalpy of the particular phase composition. Then, for each of the phase, we do the fit to find the expressions for the formation enthalpy of the phase in the form of A plus BT. And finally, we combine all the individual functions to a single thermodynamic database file while incorporating the necessary functions for the reference free energies as well. So let's dive in. So to accelerate the DFT step of the pipeline, we use special quasi-random structures, which are essentially the smallest supercell for which the correlations between the constituents and its neighbors, up to a specified number of neighbors, are close to 0. By doing so, we minimize this artificial order due to small size of the supercell by selecting the occupation such a way to have this minimum correlation, which mimics a truly disordered structure, which would otherwise need a much bigger supercell to correctly get the energies of. I shall not talk about the DFT steps of this pipeline because it really depends on the system, the choice of pseudopotential, and the desired level of accuracy. So as mentioned, the N members might be symmetrically equivalent to a higher symmetry structure. So the levels here refer to the degree of fineness of the compositional grid. Level 0 means the N members. In level 1, we have overall 50-50 composition in one sublattice. Level 2, we have 50-50 compositions of elements in both the sublattice. And in level 3, we have 75-25 in one sublattice, and then we cycle across the sublattices just as in level 1. Next, we perform the vibrational enthalpy calculation. It is usually enough to perform these for N members only. However, it can be performed for any structure. In this step, we enumerate all the symmetrically distinct perturbations given the displacement from a mean position and a particular supercell size. The perturbations are chosen in such a way that any general perturbation can be described as a linear sum of all these perturbations. Also, for this particular work, the final energies have been fit to an harmonic model, but it can also be used to include anharmonicity. We shall again not describe the details of the fit-FC code in this talk, but I highly encourage you to read the reference paper. It should be mentioned that the temperature dependence of the formation enthalpy comes from the vibrational enthalpy. And since we do not perform these calculations for all structures, we do them for the N members only most of the time, not all thermodynamic function would have a T dependence. So now we have a bunch of structures, and for each structure, we can calculate the site fraction and make an expression according to the CalFAT model up to our desired degree of accuracy. And now, provided that our system of equation is at least determinate, if not over-determinate, that is, we have more rows than the number of columns, we can perform a least square fit to obtain expression for the different N members and the mixing energy functions. We note again that since we are treating the T-dependent and the T-independent parameters separately, we confirm that since the number of data points for the vibrational enthalpies are less, the L params in this case will not have T dependence. So as you see for this work, we only have T dependence for the N members. So let's discuss the TDB file. First, we have the phase description for each phase. Then we have the functional expression for our formation enthalpy that we obtained from the previously mentioned fit. The reference energies of the constituents are measured as the difference between the formation enthalpy of the stable phase of the constituent with the SGTE free energy database. And finally, the free energy of the N members is then the difference between the formation energy of the N member and the reference energy of the individual constituents. Last but not the least, we add the excess free energy functions. We don't show it here, but as mentioned before, as a final step, we combine this energy data for each phase along with the SGTE energies to create a TDB file that can then be used to calculate phase diagrams and other equilibrium phases downstream tasks mandate. So finally, with all the setup, here we are. On the right is the latest experimental phase diagram of the iridium-ruthenium binary alloy system, and on the left is ours. So we see that there is a big discrepancy in the higher temperature, which can be attributed to A, the less accurate liquid model, and to the harmonic model that is used in the fitting of the vibrational enthalpy, which becomes a worse approximation as we go up in temperature. But what is more interesting is the things happening at the lower temperatures. As we see close to 0 Kelvin, we do confirm the existence of the stable ordered phases, but they vanish as we reach room temperatures and above due to the entropic effects, preferring the disordered counterparts instead of the ordered ones. To see the disordering in greater detail, we plot the sublattice fraction of a iridium 80 ruthenium 20% L12 phase, and we see at lower temperature, sublattice 2 is completely occupied by iridium, while 20% of the sites in sublattice 1 are just occupied by iridium. However, very quickly, as the temperature increases, the system gets disordered, and each sublattice now has iridium equal to the global concentration of 0.8. The exact similar thing happens if we see on the ruthenium-rich side of the DO19 phase. So for the iridium 0.2, ruthenium 0.8 alloy, the DO19 phase has all the iridium only at sublattice 2, but that too disorders pretty quickly to reach a global concentration of 20% in both sublattices. We do see a slight degree of persistent short-range order for DO19, but that is pretty less, as low as like 5%. To understand the ordered phase behavior, we study the individual phase diagrams. For L12, there seems to be surrounded by first order transitions, albeit very thin on the iridium rich side. For DO19, it exhibits a clear first order transition towards the iridium rich side, while the first order character completely vanishes to the ruthenium rich side. Nevertheless, this confirms our findings in the phase diagram that the immiscibility zone completely disappears at a much lower temperature than room temperatures, corroborating the lack of these ordered phases in the experimental diagrams. To further convince ourselves of the previous result, we also plot the chemical potentials of ruthenium in both phases. First order transitions show up as flat lines on a chemical potential plot. So we can posit that the L12 does have first order disorder transitions on both ends. However, DO9 on the ruthenium rich side probably has a second order transition, but we cannot be very certain of it, since second order transitions cannot be explained by the continuous functions of the CalPAD model. So what do we conclude from this? First of all, we do see that our software pipeline can produce a convincing phase diagram from pure first principle technique with a small number of DFT calculations, albeit having a good degree of accuracy that can be further enhanced incrementally. Secondly, our construction for the iridium-ruthenium phase diagram helped resolve the high throughput prediction of ordered phases being present that were not previously observed in experiments. The punchline is just that these DFT predicted ordered phases simply disorder due to entropic effects of temperature. So can we use this model to predict order-disorder transformations? Certainly not. There are other methods such as the KKR-CPA, which have shown promising results. However, the regime where our technique really shines is as a screening procedure in a high-throughput pipeline, where we can quickly perform preliminary tests to check of certain candidate phases whether they would exist, or would they disorder to some other phase at the temperatures of interest for engineering application, and thus be given less priority in the search space for competing phases in those high-throughput pipelines. With that, we come to the end of this talk. Here are the references for all the individual formalism, models, and codes used in the work. Thank you so much for hearing, and feel free to email me with further clarifications and questions. Thank you again, and wish you all the very best.